Hello, everyone. My name is Maxine Calle, and I'm getting my PhD here at Penn in math. And usually when I tell people that, the response that I get is something along the lines of, wow, I really hated math in high school. And I mean, yeah, if your high school was anything like mine, most kids hated math. They found it difficult, boring, worst of all, completely useless. You'd hear things all the time like, oh, I'm just not a math person, or why are we learning this stuff? I'm never going to use this in real life. And okay, if you press people on it, maybe they'll say that math is good for things like doing your taxes, or balancing a checkbook, calculating the tip, or making and converting measurements. But saying that all there is to math is arithmetic is a bit like saying all there is to music is scales and chords. In my time studying math, I've come to learn that there's a whole universe out there that goes way beyond arithmetic. This universe of math even goes beyond things like calculus or statistics or the other kinds of math that we encounter when learning the sciences. Math encompasses a vast array of concepts that can answer both concrete and abstract questions. My research falls on the abstract side. I study a kind of math called algebraic topology. It's over there. Topology is the mathematical study of shapes, both familiar shapes like polygons and cubes, but also strange higher dimensional shapes that are tricky to visualize. Unlike in geometry, topologists don't care about rigid measurements like angle or distance or size. Instead, we say that two shapes are topologically the same if we can get from one to the other by some kind of elastic deformation, things like bending or squishing the shape, stretching it out. What you're not allowed to do are things like tear it into pieces, make holes, cover up holes, or glue parts of the shape together. For example, there's a classic joke amongst mathematicians that a topologist can't tell the difference between a coffee mug and a donut, because you could imagine taking the coffee mug and sort of smoothly deforming it around the handle until you got a donut. The idea of topology is to try to abstract away the superficial features of the shape while still preserving its most essential structure. And you know, the thing that surprised me most while doing my PhD in math is how little what I do now looks like the math that I did in middle and high school classes. In most subjects, you slowly learn how to do the thing it is that professionals do. If you study literature, you read and analyze books. If you're in biology class, you'll do experiments. But so many math classes look so different from actual mathematical thinking. Math research is creative and exploratory, but math class is full of worksheets and formulas and rules. And so people come away from math thinking that, oh, it's just about, following some procedure or being able to do your multiplication tables really quickly and in your head. But, so many people come away thinking that they're not a math person, but I think that a lot of people secretly like math, especially when it doesn't look like math. Humans love figuring things out. We like puzzles and riddles. We love symmetry. We like finding and making patterns. And math, in many ways, is a science of patterns. This characterization of mathematics goes back to the British mathematician G.H. Hardy in the 20th century. He says, a mathematician, like a painter or a poet, is a maker of patterns. If the mathematician's patterns are more permanent than theirs, it is because they are made with ideas. And so I think, for a lot of mathematicians, this is what math is good for. It gives us a formal language to systematically study these kinds of abstract patterns. But for many students, and maybe for some of you in the audience, this isn't a satisfying answer at all. I mean, who cares? Why care about abstract patterns? And of course, not everyone has to become a mathematician. Not everyone has to care about abstract patterns. But I believe that everyone has something to gain by engaging with mathematical thinking. And I believe, moreover, that everyone deserves the opportunity to do so. And so in my time here at Penn, I've tried to seek out opportunities to share my love of math with other people and my view of it as a creative subject rather than a barrier to opportunity. I'm especially passionate about providing educational access to incarcerated individuals. Data shows that over a quarter of incarcerated or formerly incarcerated people never graduated high school. That's compared to about 9% of the general population. Some prisons offer education programs that students can enroll in and work towards earning their GED or a college degree. And studies have shown that these kinds of education programs are extremely impactful in reducing recidivism rates and saving taxpayer money on incarceration costs. However, access to education in prison is extremely limited. Following the 1994 crime bill, which banned incarcerated individuals from receiving Pell Grants, these programs were severely impacted, going from nearly 1,000 programs operating in the country in the 1990s to just 12 programs and 12 facilities by 2005. Only since July 2023, which is nearly 30 years after the original ban, are incarcerated individuals finally eligible for federal financial aid to help pay for their higher education. In my time here at Penn, I volunteered with different prison education programs, both as an instructor and a tutor for college-accredited math classes. I've worked at Southwood State Prison and Garden State Youth Correctional Facility in New Jersey, as well as SCI Chester, which is just outside of Philly. This semester, together with some other graduate students in the math department, we taught a workshop called Math in the Courtroom at SCI Chester. Over the course of 7 weeks, together with our students, we looked at how math appears in legal contexts, how logical arguments are built, how statistics and probability have been used or misused in the court, and how graphs can be manipulated to tell different stories using the same data. And now the goal of this workshop wasn't to turn anyone into a mathematician. Rather, it was to help our students gain confidence analyzing quantitative information, breaking down complex problems into smaller pieces, and most importantly, showing them that they can learn math even when it is difficult, unfamiliar, and confusing. When we surveyed the students at the end of the workshop and asked them what was something they had learned, one of them said that you are never too old to learn math, that mathematical ideas and concepts can be applied to almost anything. Teaching inside of prisons has forced me to rethink what math is actually good for, not in the sense of practical applications or in some romantically academic way, but in the sense of what it actually does for people. And so what do I think math is good for? I think math is good for fostering our creative thinking skills and problem-solving skills. It's good for fostering curiosity. And most importantly, math forces you to be uncomfortable and to not understand things. Doing mathematics is extremely humbling. Everyone at some point encounters some math concept that they don't understand and they have to work hard to figure out. When people ask me what doing math research is like, I like to tell them that my job is being confused 80% of the time and wrong the other 20% of the time. There's this quote that I love by a math professor named Courtney Gibbons. She says, "Being good at math is being good at being stuck and thinking, okay, what's the next step?" At its best, math can help us learn to push through and not give up when things get hard. And it can give us compassion for those around us that are struggling to do the same. And I think that at this time in this country, that is something that can be good for all of us. Thank you.